In this video we're going to look at some layered data, reinsurance layered data, and we're also going to take a look at the PALD, predictive aggregate loss distribution module. So let's begin. We'll open workbook 104 and we'll choose these three triangle groups here, all 1M, all 1M, excess 1M, and all 2M. So in the all 1M triangle group, the claims have been truncated at $1 million. So claims under $1 million are counted completely. Claims that come in above $1 million, the first $1 million is counted there. They're truncated at that point. The all 2M, they're truncated at $2 million. And all 1M excess 1M is the excess above 1 million for the claims which go above 1 million up to an excess of 1 million. So in fact the sum of the first two, the triangles in the first two triangle groups equals the triangle, the paid loss triangle in the third group there. So I can open these three triangle groups either by clicking on triangle group button here or by right clicking and just activating open there, control enter, and then I'll minimize database view and get the three triangle groups side by side. Now these three each have a model, the paid losses each have a model called good, which in fact is the same model that's been copied across. So let me open each of those good models. And we'll take a look at them. So let's begin with minimize regression tables, and that gives us the three models with their associated residual plots side by side. Now just to begin, I'm just going to look at the three calendar year plots here. Let me enlarge these so they fill the entire screen. I can just minimize other types. So this gives us some idea of how similar these groups are and yet how different. The shape of these calendar year plots has quite a lot in common, but if you look closely you'll see the dots are all in different positions. So it's different data, but at least at this level, after the trends have been removed, it appears to show a similar structure. In fact, the trend structure is a little bit different in each case. Restore those. Let's enlarge the model displays. So I just right-clicked here and then clicked at all, so that put the three model displays back again, and now I'm going to minimize other types to get the three model displays side by side. So the same model with parameters in the same positions. You'll see that the parameter estimates are a little bit different from case to case. But what's most interesting is the difference in the calendar trends. So in this case here, the all 1M, the ground up data up to 1M, shows a calendar and inflation rate of 10%. The all 2M shows an inflation rate of 8.7%, so somewhat lower. The layer data, which is the amount that might be hived off for reinsurance, shows a 5% plus or minus 4, 5.6 plus or minus 4.3, the standard deviation of 4.3%, considered insignificant. So if we were to optimize or run a wizard model, this trend would probably have just come out to 0. However, in a case like this, I don't know if we could be completely satisfied with allowing this trend to go to 0. Firstly, we might be using this model here for pricing the layer, in which case we want to get a conservative estimate of what it can do. And secondly, we may not have enough data to actually pin this trend down. We can see quite a substantial trend in the two other segments of this, and so it wouldn't be very wise to think that all the trend had been completely removed in the layered data. So when we do run our forecast, we will stick with this 5% plus or minus 4, but it will affect the size of our forecasts significantly. So if I forecast using this calendar trend, I'm forecasting under the assumption that the iota, the inflation rate, is a random number drawn from a normal distribution with this mean and this standard deviation, which means that a substantial fraction of the time it's 5% or higher. It may even be as high as 7 or 9%. Also, a certain fraction of the time it's lower than 5%. But the overall average will be affected more by the higher inflation rates than by the lower inflation rates. That's the skewness, due to the skewness of the log normal. So let's just enlarge this one. Let's put those two down. Now, when we do our forecast here, if we're considering, say, pricing, we might want to look at some future accident years. So let's put 3 future accident years here. The exposure is to put down as 1, and that's because the original exposure vector was all 1s. So we don't have any information here. We're not putting in any information about what we expect the relative sizes of these future years to be. We could, of course, in future parameters, now that we have some future accident years, we can click our Changing Alpha tab and we can put in estimates of how we think the accident year levels are going to change. Now remember that we're forecasting with a calendar trend of 5%, so built into this is already the idea that each future accident year is going to be 5%, start out 5% higher than the previous accident year. So if we're happy with that assumption, we'd just leave this. But if we wanted to say, well, no, I think that the following year it's going to go up by 8%, not 5%, then we might put 0.03 here, and with a certain attendant degree of uncertainty, say 0.1. And then we might think, well, it'll go up next year by 8%, and then it will just continue at the 5% underlying inflation. So we might make an assumption like that in our forecasting. Let's stick to that. Now, when we produce our forecast, we have this tick box here, which I'll activate, Combined Forecast Tables, and that means that my forecast table will have the 3 new columns in it, as well as all the 3 new rows for the future accident years, as well as the past accident year. In fact, I'll have the option of 3 different forecast tables. So let's click OK here. And the table that comes up immediately is the combined forecast table. So this has the 3 extra years here, and you can see that well, you can see if you look at the first development period, well, some years we don't have any data there at all. The black numbers here are the model estimates. Notice that here in 1998, the observed was extremely high, but this is reinsurance layered data and quite volatile. The forecasts in the following years are somewhat closer to the observed. The standard deviations here are very high, so this 459,000 is not completely unexpected, even though the underlying mean in the forecast was only 2,800. But here we see the underlying means here gradually increasing. This is this 8% increase followed by these 5% increases. As we move along to the later development years, the numbers get very large, so any volatility that occurs early on is soon swamped by the high volatility in the later periods. We can see this again if we just look at the model display and see that, in fact, the first development period is very low. The losses here peak about the third year and continue very high for 4 years after that. So that was our combined forecast summary. We also have the option, the combined forecast table. We also have the option of the future accident period forecast, which only gives us the 3 years of interest and just the reserve forecast table, which gives us the reserve figures there. Similarly, we have those same choices with the forecast summary. The future is future accident forecast summary, FAF. So inside these, of course, we have for each way of looking at it, we have the accident year summaries and the calendar year summaries and various other comparative statistics here. When we look at the future accident forecast table, this one here. So here for each of these 3 forecast years, we have summaries by calendar year and summaries by accident year, and these are the future calendar years. And the numbers in each of the forecast cells are, well, each cell is given a log normal distribution with this mean and this standard deviation. So how do we know that that's a reasonable assumption to have made about the future cells? Well, we can assess that on the basis of the original model by looking at the normality diagnostics for the original model, which is this table here. And we can see that relative to the trends that were identified in the model, the residuals, in fact, display quite close to the normal distribution. I mean, the probability that these numbers were drawn from a normal distribution is greater than 50%. So this display looks a little skewed, but this PP plot is very close to a straight line. So we're reasonably happy about the normality assumption. However, let's go back to this future. We may want to have more detailed information about the distribution here. For example, in 1999, we're forecasting a mean of 48 with a standard deviation of 48 million with a standard deviation of 20 million. But this represents the sum of these log normals. Now, we've calculated this 20 million standard deviation because we know the correlation between these cells. However, we don't know the distribution that's behind these particular figures, because the sum of a collection of log normals doesn't have a distribution that can be reduced to some well-known distribution function that depends on the precise differences between the log normals concerned. So to get some idea of the shape of this distribution, in particular how large the tail can be, we need to go into the predictive aggregate loss distribution module and use that to simulate these results. And what it will do is simulate however many we require. 10,000 is the default values for each of these cells, then add them all together, and then when you look at the distribution of the sum, you get a distribution curve which you can extrapolate out into the higher quantiles. So let me do that, and I'll do it in a slightly simpler way by changing the forecast so that it only has a single future accident period, just 1999, and but I'll stay with this 3%. So I'm assuming that 1999 is going to have 3% above the 5% inflation factor that it belongs to the model. So and the result should come out to 48,258,505 because the individual accident years are not correlated. So merely having those other future accident years is not going to affect whether they're present or not. Isn't going to change the value I get for 1999. So let's open up the future accident period forecast, and there it is, the same figure there. So now I'm going to run PALD, and I'll click here for future so that the PALD will only look at that 1999 result. So it's going to simulate, in this case, 10,000 results there. And if I wanted to do further work with these simulations, I could, in fact, ask the program to save them as a text file. And this is a tab-separated text file that you can open up in Excel. Although, of course, if you do more 100,000 simulations and you're working with Excel that's limited in the number of rows it can display, you're not going to be able to display all of that data. So if I was to leave this box ticked and then click OK, I'd be prompted for the name of the text file to save these simulations. So now let me click OK here. And the first screen here gives me the summary of the... I'm now, having done PALD, I'm now in the display PALD window here. And the first screen here is the summary. So the true mean was 48,258,505. The mean of the 10,000 simulated values is 48,346,088. So that's pretty close. It's certainly close enough. The sample standard deviation is 20,809,000. The true standard deviation is 20,712,000. So our simulated values came in as we expected. Now, here in this table, there are 10,000 rows, and each row says what the total for 1999 was in that particular simulation, and so the two numbers, in fact, in the two columns are the same since there's only a single accident year being forecast. So we can scroll down that table if we want. We can also change the periods, select PALD periods, look at the calendar years, and again, if I click OK for total, then in each of the simulations, for each of the 10,000 simulations, it tells me what, according to that simulation, I would have paid in each of these future calendar years, right up until 2012, which was my 2012, my last calendar year, and then we have that same list of totals. So I get that analysis there. I could also choose an individual calendar year, 2009, and then this table is unaffected, but the other summaries change and just concern 2009. Let me just go back and get the total again. In fact, I'll just move to accident year totals, so I can go through the rest of these tabs. This one is the quantile summary, and again, since there's only one accident year, I get just the summary for that year, but if there were more accident years, I'd get the quantiles for each of those accident years. I get the 60th percentile, the 75th, the 85th, and so on, the 99th. I can actually, by right-clicking and set percentages, choose any other percentage that I want in this list. I can also remove percentages from the list, but let me put in 99.5, that being a popular percentage, and it shows up in the list in the correct position. So although my mean was 40-something million, my 99.5 percentile is 131 million, very much higher than the mean, of course, because we had a standard deviation of 20 million, which was itself fairly high. This also suggests that the distribution is skewed. So if I go to this tab here, I get a picture of that distribution. Here's the density. And you can see that it's quite a skewed shape. The colors here, the purple represents the gamma. I'm going to hide that. And the green represents log normal. The blue represents what's called the kernel distribution, which is a smoothed version of the actual data. So let me remove that. And now what I have is this gray, which is the actual data. This is a lumpy, uneven looking graph because it's based on the 10,000 simulated values. If I was to have done 100,000, this graph would have been a little bit smoother. Now the red line and the yellow line represent the mean and the median, respectively, based on the simulated data. And the thing to observe here is that the mean is significantly to the right of the median, and that is an indication of skewness out in this positive direction. And that means that even though half the values are below the yellow line and half of them are above, the half that are above tend to influence the mean. They're much further out in the plus side than the ones that are smaller than the mean are on the minus side. Or another way of thinking of it is that the mean is, there are more than half the values are below the mean. In fact, we'll see what that percentage is in a minute. Now if we look at the other distributions, if I click gamma, that fits the gamma distribution to the same mean and standard deviation as we got from the analytic, the actual model forecast table. And you can see the gamma fit's not really very good. It's not quite catching it there. The gamma is a very light-tailed distribution as well, so a bit dangerous to use that. The log normal actually fits it quite well, at least to the eye, but when we look at the higher percentiles, we'll see that it doesn't quite catch those either. The kernel, being a smooth version of the actual data, is always very close to the data itself, and is generally, I think, quite good for use for the higher quantiles. So let's now click this tab, which gives us the quantiles table. And now what we have is that for each of these four ways of looking at it, the sample itself, the kernel, smoothed version of the sample, the log normal, and the gamma, we get the value of the quantile for each quantile, the standard deviation of that quantile, the value at risk, which is the loss at that quantile. So let's take, for example, the 99 percentile. So in 1% of cases, the loss will be greater than or equal to 119,923,000. Now in this case, we've set our provision equal to the mean, so we've put aside 48,259,000. So if we do fall into this 1% or worse of cases, then we will have lost at least 71,664,000. We have that much put aside. Our actual loss came to this. So this was our value at risk at that percentile. Of course, the value at risk depends on what you assign as the provision. The default is that the provision is set equal to the mean, but we can change the provision by right-clicking and going up here and put any number that we wish. For example, let's say we provisioned at 50. So if we provisioned at 50, the value at risk, of course, would go slightly down. The tail value at risk, the value at risk, let's go back to the 99th percentile. Here the value at risk was, well, by provisioning at 50, the value at risk has gone down from 71 to 69.9. The tail value at risk is the average loss, the expected loss if you know that you're in at least the 1% of worst cases. So the value at risk is a little bit deceptive in that if I am considering what happens in the 1% of worst cases, the value at risk gives you the threshold. I know I'll be at least as bad as 69.923 million. The tail value at risk is what my average loss, or my expected shortfall, which is another name for it, will be if I am in that 1% of worst cases. So if I fall into the 1% of worst cases, I can expect my average shortfall, my average loss will be 86 million, which in this case is considerably greater than the 69 or the 70. Now, if we remember, we saw that the mean was somewhat above the median. If we scroll down the table and we find the red entries here, these tell us where the mean. Well, these two entries straddle the mean, so the mean is somewhere between the 58th and the 59th percentile. It's 48.259, and that comes in around here. Also, scrolling up again, let's just take a look at how the high, the value at risk at the very high percentiles, like 99.99. And here we see that the well, here actually the value at risk from the log in the log normals are quite a bit higher than the value at risk from the kernel. Whereas the value at risk in the gamma being a light-tailed distribution, is much lower. So this would be dangerously lower assumption if one was serious about the 99.99th percentile. The data itself, the value at risk is 136, the kernel's 145, the log normal, which perhaps doesn't fit all that well at these high percentiles, is 154. Perhaps that's a little bit too high, so probably the safe bet would be to go with the kernel there. So remembering that this is our layered data, so it might be used for reinsurance, or reinsurance might be applied to it. Let's go to the reinsurance module, which is this one here, and click this button. And now let's imagine that we've provisioned at 50. So, and that anything above 50 we've reinsured with the next 20. So if it's between 50 and 70, then reinsurance is going to cover that difference, that 20. Then if it comes in above 70, well, we take that back again. We retain that. So the reinsurance module enables us to calculate this based on the simulations. So if I click OK here, it takes a few seconds, it runs 10,000 simulations, and now I have this table. So for each of these future years, this is just for the accident year 1999 here, we can see what the expected losses are in those years, and we can see how much the insurer retains. In the early years, the insurer retains all of it. In future years, sometimes it gets above our mean, and then the reinsurer takes some of that risk on. So the total after 2012, the insurer's mean drops to 43 million, and the insurer's CV drops from 43% to 34%. The reinsurer's mean is 4.8 million. Standard deviation, though, is extremely high, 7.5 million. Their CV is 1.56. So the reinsurer takes a very volatile layer there, which is essentially what the reinsurance is for. So in these other tabs here we have, well, this gives a distribution for the layers. This is the VAR and TVAR for the insurer at the different percentages with the same color coding here. So it's fairly rare. Mostly the insurer would expect to pay the 50 million, except of course if the aggregate of the claims gets above 70 million, then the result comes back to the insurer, and so the insurer's quantiles go up. So in some of these very high quantiles, the insurer, well, they've offloaded 20 million to the reinsurer, but they've still had to take up the remainder. Similarly, we get the reinsurer's quantiles, and of course these stop at 20 million here, only at the low, or between the 62nd percentile and the 87th percentile. The reinsurer's share moves between 0 and the 20 million, the full amount reinsured. Here we have a table of all of the 10,000 simulated values, and here we can see this is for the insurer, and this one here is for the reinsurer. So we can see all these years in which all these simulations in which the insurer pays their maximum, and the occasional simulation where the insurer pays the maximum of 50 plus in this case another 59 that comes back after the reinsurer has covered the 20 intermediate million. If we look at the reinsurer's version of the same table, we can see the occasions when the reinsurer pays their maximum, which occurs fairly often in this table. So using this table, we could work out proportions such as how often does the reinsurer pay anything at all, and given that the reinsurer is going to pay something, how many times do they pay their maximum? Now these are figures we could also estimate from the PALD, from this table here, the distribution table. The proportion of times that the reinsurer pays anything at all in this scheme is the proportion of times that is the percentage of times the mean is above 50, because we've set the provision at 50 here, so it's roughly 38% of the time the reinsurer has to pay something, and of those occasions when it gets above 70 million, it's about 13%. So if we actually divide the 13% by the 38%, which is roughly a third, that tells us that roughly a third of the occasions when the reinsurer pays anything at all, the reinsurer pays the maximum 20 million in this particular arrangement that we've created. So we can check to see if that's borne out in this table here. If we wished, by counting the number of non-zero entries and the number of 20s amongst the non-zero entries, which I could do in Excel, but It's a bit of an extraneous exercise at this point. The point of all of this is that any kind of analysis that you need to do of the way your reinsurance has been set up can be done when you have these complete simulation tables. Anything that can't be done directly in ICIFIS can be done by saving the simulations to a text file and then processing the text file in some other program. Okay, well that's an introduction to PALD and to the reinsurance module, and that ends this video. Thank you.